Good afternoon. Welcome to the sound and video check for the ENGG1003 lecture. We'll kick off in a few moments, but I just wanted to check that you can both see the screen, the title page for the Thursday week 9 lecture, and also hear the audio. So we should be live streaming on YouTube now. Someone give me a thumbs up that in the questions lectures channel that you can either. Wonderful. So I'll post a couple of questions there to separate the audio from the video. Start with the audio. Wonderful. Thanks, Tyler. And just checking that you can see the title page. For Thursday, week 9. Wonderful. That's great. I'll go offline for a few minutes and we'll kick off with the lecture at 4:05. See you then. Okay, good afternoon. We'll kick off with the lecture now. I'm assuming it all's good with the audio and the video, so let me know otherwise on the questions lectures channel if there's any problems. I'm not sure if either Sarah. Wonderful, thanks very much. I'm not sure if Sarah or Brenton will be on the channel this afternoon. I'll try and keep an eye on the channel and answer your questions as best I can as we go. Okay, so the content of today's lecture is going to make a link between two topics that we've seen previously. And it's probably an unexpected link if you haven't seen it before. It follows on from Monday's lecture, and which in turn follows on from last Thursday's lecture, that where we use numerical integration to compute the area under curves that arise in applications. Sometimes those functions, depending on how they're defined, might have, it might be possible to compute the area exactly. Oftentimes in engineering, that's not the case. And we find one of those cases today. And the other link with the material we've seen before is in the form of random numbers. And so we saw random numbers in particular types way back in week 4. And this week's assessed lab is indeed getting you to exercise some of that capability with randomly chosen integers. You also, if you think back to week 4, which seems like forever ago, but in week 4, we introduced what were known as uniformly distributed random variables. So these were random numbers that could take any value within a specified range and would do so with equal probability. We're going to, in today's lecture, look at a more sophisticated form of distribution of random numbers, and it's known as the normal distribution. It's also known as the Gaussian distribution and informally known as the bell curve. So even people that haven't studied statistics at all, and I don't expect you to have done any statistics at all in this course, even if you haven't studied statistics at all, you're probably familiar with the idea of a bell curve where numbers fall within a range and they concentrate around certain values. And then as you get further away from that central value, the likelihood of observing that particular number decreases. So for example, if you were to plot a list, if you were to tabulate people's heights, for example, they would be centered around some average height, and the further you get away from that average height, the likelihood of observing someone with a particular height would diminish. So we're going to look at the normal distribution today. We're going to introduce it. And one of our two goals is to be able to draw random samples from a so-called standard normal distribution. And I'll say exactly what that standard normal distribution qualifier means in a slide or two. So the first thing is we're going to be able to draw numbers using Python. We're going to be able to draw numbers from that distribution. And the second thing we're going to be able to do after today's lecture is compute probabilities using these normal distributions. And we're going to use numerical integration to do that. So what about this normal distribution? We're going to introduce a restricted form of it today, just to keep the discussion very focused, and we'll generalize it next week to a more general form, a more useful form, and then we'll apply it in some engineering settings next week. So I just want to do two things with you in this Thursday lecture, and they're both Python related. One is to be able to draw random samples from these standard normal distributions. And the second one is to be able to compute the probability of a random number falling in a specified range when it follows this so-called normal distribution. And we're going to do that. We're going to do that in a very hands-on way, because I want to allay any concerns you might have that you haven't studied statistics before, and some of the mathematical expressions that you see later in today's lecture, if you haven't got a sense, a feeling for what they mean before you see them, they can be a little bit off-putting. So I want to start with something very concrete and show you in a very hands-on way what it means for numbers to follow this so-called standard normal distribution. So what we're going to do is we're going to generate 100,000 random numbers using the normal function in NumPy's random library. And I've mentioned a couple of times now, we're going to focus on what's called the standard normal distribution. And the standard is a special case of the more general normal distribution we'll look at this week. And for the purposes of today's lecture, I'm not going to talk about interpretation. I'm just going to give you the parameters which allow us to fix our consideration to the standard normal distribution. So in the middle of the slide that you see there before you, you'll see that the call to the NumPy random normal function uses 3 parameters. And I've indicated the first 2 in color, a red 0 and a blue 1. For the moment, for today's lecture, we're just going to use those parameters. I won't say what they mean. I won't give them an interpretation. I won't give them name. I won't give them anything. I'll just say that's what defines a standard normal distribution when we choose the first number to be 0, the second number to be 1. Don't worry, suppress your excitement, because on Monday we'll generalize those 2 numbers and I'll show you the effect on the distributions. The third parameter that we need to pass into the normal function in NumPy's random number library is a size parameter, and that tells us how many random numbers to generate. So in this case, we're going to generate, 100,000 random numbers and put them in an array, a NumPy array called X. And then we're going to use another function from this time matplotlib, and it's called hist. And hist is short for histogram. And a histogram is going to be able to allow us to make some sense of those random numbers by putting them into bins. So this is just a little heads up on some code we're going to run live. Generate 100,000 numbers and interrogate what they look like using the histogram function. And we'll observe something really interesting, and then we'll pick up at that interesting point and complete the lecture. So I'm going to do about, I think it's four different experiments. They're all variants of the same experiment. And they all use this code histdemo.py. And I've pasted this in Blackboard's week 9 course materials and also in the lecture code channel a short while ago. Now I'm going to break with tradition here a little bit, and I'm going to give one set of code, and by successively commenting out lines in that code, I'm going to step through the 4 different scenarios that you see here. So let's do that now. We'll do it live, and then you'll be able to see in the lecture notes what the 4 scenarios are. So the first one is we're going to run hist demo. And what I want to do on the first one is generate. Okay, so you should be able to see there on the screen code where a number of the lines have been commented out. So the only lines that exist are the 2 import statements on the first 2 lines. I'm also going to set the random number seed. And the reason for that is I want you to be able to reproduce exactly the histograms and the curves that you see in the lecture notes. There's nothing otherwise special about that seed. I could have chosen any number, but I do want you to exactly replicate these if you chose to. So we're going to generate 100,000 random numbers and put them in a NumPy array called D. And then the key line in this code that you see here before you is line 11, where we plot a histogram where the second number 10 specifies the number of bins. So I'll show you what that means. We run hist demo. You can see there what's known as a histogram on the screen. So you'll see what happened is I generated 100,000 numbers, and then the histogram function used 10 different bins. It looks like there's less than 10, but if you zoom in, you'll actually see there's a bin down here around -4. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and another little bin around 4. So what that's done is take the 100,000 numbers that were generated by the call to the normal function in the NumPy library, and count up the number of occurrences in each of a number of bins. Now, it's possible to get tricky with histogram and specify the bin edges. Don't want to do that today. All I want to do is specify that there were 10 bins. And you can see that, for example, in the bin that is just above, it means that the values of X was somewhere between 0 and 1-ish. There are about 30,000 of that, represented by the height of the blue histogram there. So the height of each rectangle is reflecting the number of samples that have fallen in each bin. And if you added up the total number of samples that were observed in all the bins, you get to 100,000, because that was the number of random numbers that we generated. Just bring that up again. So there's roughly 30,000 that are a bit above zero, about 28,000 that are a bit below zero, and so on. So what you observe in those random numbers is that most of them take value around zero, and as the number gets bigger, up towards 4, or smaller, down towards -4, there's very few occurrences of them. So that's the nature of what the histograms are doing. They collect the histogram function in the hist function in the matplotlib library simply counts up the number of occurrences in the different ranges, and we specify just the number of bins. I'm now going to rerun that code, same code, but this time I'm going to change the number of bins from 10 to 100. And because I'm using the same random number seed, I'm getting the same random numbers. All I'm doing is changing the number of bins from 10 to 100. Let's run it again. And we see something really interesting. We see a classic bell-shaped histogram. It's the same data, it's just that we're using narrower bin widths now. So now, if you look carefully on the vertical scales, you will observe that there's fewer values occurring at the most frequent, the most populated bin, but the bin width is smaller. So roughly the bin widths, the bin width is 1/10 the size, but the height is also 1/10 of what it was. So it's the same data. I've just grouped it into 100 bins, and now we're starting to capture what normally distributed random numbers are. They mostly take values around zero, at least the standard normal. And the further you get away from zero, the shorter the histogram bin height is, meaning that the fewer occurrences of those numbers occur. Now, it's possible using the standard normal distribution to get a number that's at 4 or 5 or even 6, but it's really unlikely. And so we'd have to run a very large number of draws from that random distribution in order to get any sort of appreciable number of occurrences that were very much greater than zero or very much less than zero. So all I've done so far is draw those 100,000 numbers and pop them into either 10 bins or 100 bins. Next modification I'm going to make is I'm going to if you look in the code, I'm going to call the hist function with a third parameter. I'm going to say density is equal to true. What that's going to do is normalize the histogram. Let me run it again. Same code, same random numbers, same shape histogram, except now because of this call to the density with the call to hist with the density equals true, it's actually shrunk the heights of each bin such that the blue shaded area has been normalized to be 1. It's the same histogram as we saw before. All that's happened is that the hist function has, with the density equals true option, has shortened the heights so that if we added up the area of all the 100 rectangles, the area of the height, the width times its height, the area of that blue shaded bell curve that you see in front of you would be equal to 1. 10 bins, 100 bins, normalized histogram with 100 bins. We've got one step to go. And with that step, what we're going to do is we're going to also plot a histogram which has been normalized. And we're also going to uncomment lines 8 and 9 and also uncomment line 13. And what that's going to do, lines 8 and 9 define a function which we haven't seen before. It'll come up repeatedly in the rest of today's lecture. It's quite a complicated function. I won't go into the detail here. It'll look clearer as to what that function looks like when we revert to the PowerPoint slide with the PDF slides in a moment. So we're plotting a normalized histogram, and in lines 8 and 9 we define a function f as a function of x, and on line 13 we plot that function as a red line. So let's run that now. And what you see before you is something really interesting. It's the histogram we've seen in blue, normalized, overlaid with this red function that I dragged from nowhere, but we'll discuss in detail in just a few minutes. That red function is what's known as a probability density function. It's a function that's going to allow us to do a couple of things. One is describe random numbers that satisfy this so-called standard normal distribution. And it's also going to allow us to calculate the probability of random numbers falling in certain ranges that satisfy this probability density function. Now, you might ask why we need such a thing as a probability density function. And the reason is that for random numbers such as integers, such as, for example, when you're rolling a dice, there are only 6 outcomes, and each of them occurs with equal probability, at least for a fair dice. So the probability of rolling a 1 on a dice is 1/6. The probability of rolling a 2 with one dice is 1/6, and so on. When we've got random numbers that are not integers but fall within a certain range or are specified by over a continuous range, the probability of observing any particular random number is actually 0. So we need to be more sophisticated in the way we describe the way that we're capturing these random numbers. And a probability density function allows us to be more precise. The reason I've presented the information in the way that I have, through building up histograms and then overlaying the probability density function, is because I want you to think about a probability density function in terms of tiny little histograms that go to make up that shape. And the reason for that is tiny little histogram bars, I should say, that make up that shape. And the reason for that is the probability density function is going to allow us to describe random numbers that fall within certain ranges. In other words, random numbers whose histograms have certain areas where you to add them up. So let's revert to the lecture slides now. And what you see on the slides here, on slides 6, 7, 8, and 9, is that sequence of 4 experiments done with the same Python code. You can replicate these results because the code's been posted in lecture code. It's also been posted on Blackboard. Really key slide that you see in front of you there on page 9. It captures the idea that a probability density function describes random numbers following this so-called standard normal distribution. And here on slide 10 is the expression for the standard normal probability density function. Looks pretty complicated if you haven't seen it before. Just for the moment, just ignore the fact that there's this 1 on square root of 2 pi sitting out the front. The standard normal probability density function, which is this red curve, actually looks like e to the minus x squared on 2. And if you were to just plot that function, you would get the classic bell curve. For large x, e to the minus x squared on 2 becomes approaches 0. In fact, that's true if x is negative or positive. So the standard normal probability density function takes this form. It says for any value of x, it allows you to plot a point on that red curve. Notice what it doesn't say. It doesn't say that the probability of getting a random number x is at the value on the right-hand side. Nope. What it says is that the boxed equation is the red curve. And we know that these probability density functions have got something to do with the area under them somehow capturing the likelihood of observing a number in that range. And I said earlier that this standard normal probability density function corresponds to 2 particular parameter choices in the call to the normal function in the NumPy library. And again, I'm using color here to draw you right at the fact that the first parameter is something that will use the Greek letter mu next week. And the second parameter in blue is something that we'll call sigma. Don't want to talk about their interpretation today. That's for Monday's lecture. But just to let you know that the standard normal probability density function, or PDF, is a special case of something where next week we're going to be able to vary these red and blue parameters and observe a shift in the shape or location of that curve. So just for a moment, we've talked about this very special case. It's special, but it's really important, the normal distribution, and in the particular case of the standard normal. Just for a moment, just for 2 slides, we're going to talk about some general properties of these probability density functions, otherwise known as PDFs. PDFs are able to very compactly represent random numbers. So x is if x is a random number drawn from a distribution with a PDF of f as a function of x, we've seen a special case of it here, but this is for the general case, then the probability that x takes a value in the interval a to b is represented by the integral of that function f. Now, we've spent quite a bit of time in lectures over the last on Monday and also last Thursday thinking about integration. And by now, I hope that you're starting to think about integration in terms of area. Here's an area interpretation of these PDFs, these probability density functions. And in fact, the area is going to be the probability, which is really powerful. So if we have a probability density function f, and we want to know, and it can take a general form, it's going to satisfy a couple of properties. They're on the next slide. Just suppose we're given a probability density function f, and we want to be able to draw random numbers from that probability density function, and then ask ourselves, what's the probability that a random number chosen from that distribution takes a value between a and b, where b is greater than a. The boxed equation says that that probability is the area under the f curve between a and b. So the probability of the random number falling between a and b is the integral of f over the range a to b. And the graph that you see at the bottom of the slide here on bottom of slide 11 captures that in a visual form. For a general f, we're not saying what particular form it takes. Could take a normal distribution, could take some other form. Doesn't matter, just a general f. For a general shape f, for the random number to fall between the ranges a and b, we need to calculate the blue area, the blue shaded area, because that's the integral of f over the range a to b. And that integral, the area, the blue shaded area, is actually the probability, which is really nice. What it does say that the probability density function, the PDF, has to satisfy a couple of properties. One is that the total area under that blue curve, under that curve, has to equal 1, because the total area under the curve represents that the probability that the random number takes some value somewhere between minus infinity and plus infinity. So not just any old function can serve as a PDF. They've got to have area 1 underneath them. The second property that the PDF needs to satisfy is that the function f has to be positive, or at least non-negative. It can be 0, but it can't be negative. And the reason for that is, if it was negative, then it wouldn't make any sense if we could integrate over certain regions and find that the probability was negative. That doesn't make any sense. So there are two key properties of PDFs that need to be satisfied by any function that's served up as a potential PDF. They have to be positive, or at least non-negative, and they have to have area under them 1. And I've said that in words. There it is in maths, if you happen to like maths. What I do want to draw your attention to is the very final line on this slide 12. Remember I said before, ignore this 1 on square root of 2 pi factor in the standard normal PDF. Ignore this term out the front. Now I don't want you to ignore it. Now I want you to think about it. The reason for that is that this f of x with this scaling factor here guarantees that the area under the bell curve, the area under the standard normal distribution, the area is equal to 1. I don't expect you to know that the integral of either the minus x squared on 2 is equal to square root of 2 pi. Happens to be, but I don't expect you to know that. But that explains why this, if you're studying statistics and random numbers, and all of a sudden there's a pi that appears out of nowhere. The reason for it is that the area, that expression in the boxed equation is the red curve, and the total area under the red curve is equal to 1. That calls for this sort of normalizing factor here. So it looks a bit mysterious. It's just the way it is. The equation that's important is this one on page 10, which is the form of the standard normal PDF. Okay. We've satisfied goal 1 for the lecture. Goal 1 was to be able to draw random numbers that satisfy this standard normal PDF. And we've been able to do that. Let me back up a couple of slides. We did that by a call to that you see at the bottom here of slide 10. A call to the NumPy random function normal with first parameter 0, second parameter 1, third parameter equal to the number of random numbers that we want. Pop them in an array. Step 1, use Python to generate random numbers. There it is on page 10. Step 2, let's think about what we know. The probability of a random number taking a value in this range A to B, if it follows the standard normal distribution, and let's look at this equation. It's got the normalizing factor of 1 on square root of 2 pi out the front. And then inside the integral, it's either the minus x squared on 2. There's our equation of the standard normal PDF on page 10. So we know that the probability of a random number that satisfies is being drawn from this distribution. How Python actually does it, not relevant to this course. But it will generate random numbers according to this distribution if we call the NumPy library normal. So the probability is given by this integral between A and B. It's this area interpretation of the PDFs. So now you say, okay, the probability of the random number x falling in the range A to B is given by this 1 on square root of 2 pi, the integral from A to B of either the minus x squared on 2. That looks easy enough. Well, it is and it isn't. It turns out that there's no exact expression for e to the minus x squared on 2 integrated between a and b, at least for not for general a and b. For special cases there is, but not for a general a and b. So now we're in the trouble. We've got a bit of trouble. We need to be able to compute an integral of an expression for which there's no exact expression. We can't use calculus, tools of calculus. No tools exist to be able to compute that integral. It's not really a problem though, because we can use numerical integration just as we did on Monday's lecture and that I introduced to you at the end of last week's lecture. So now what we're going to do is we're going to use an approximation method. We could use either the trapezoidal method or Simpson's method. Let's use the trapezoidal method. And we're going to approximate the probability of drawing a random number x somewhere in the range 1 to 2 when x is drawn from a standard normal distribution. We know how to do it in Python. There it is at the bottom of page 10. There's the call to the normal function. We know in principle how to compute the probability of a number in the range between a and b, and in this case a is equal to 1, b is equal to 2, the lower and upper limits of integration. But now we've got a situation where we need to integrate this function between 1 and 2 and then multiply by 1 and square root of 2 pi. So we're going to run the code. I've shared the code with you. We're going to run it live in just a moment. But first, I want to give you a visual image of what we're doing. The question is to compute the probability of the random number falling in the range 1 to 2. That's what this P stands for, it's probability. What's the probability when x is drawn from the standard normal distribution? What's the probability that the number falls in the range 1 to 2? What you see here on page 14, the blue curve is no more than this standard normal PDF. It's the same curve as the red curve that existed in the first example in today's lecture. Standard normal PDF, there's only one of them. It's the blue line, the blue curve. Now the red shaded area, notice that the red shaded area spans from x equals 1 to x equals 2. That red shaded area is equal to the, it's the area under the standard normal PDF between x equals 1 and x equals 2. Now, at the bottom of this slide, slide 14, I've given you the number that comes out of the code that's going to be on the next couple of pages, and we're going to run it live in just a minute. So the red shaded area is equal to about 0.1359. That's the 4 decimal places. That's it as a number. The interpretation, because the blue curve is a standard normal PDF, the interpretation of the red shaded area is that it's the probability of a random number that's drawn from that distribution taking a value between 1 and 2. That's this area interpretation of the PDF. Page 11, it's in general form. On page 14, it's a very particular form, standard normal PDF, where the A and B take the values 1 and 2. So what we're going to do is I'm going to present the code for you, pick out the main points in it, run it live, and then do a verification that the answer we get makes sense using another piece of code, again, that I've shared. And that'll be today's lecture. So here's the code. It's called standard normal.py, and the problems are getting interesting enough now that the code splits across 2 pages. This code, only a moment's glance at it will tell you that you've seen it all before. The only difference here to any code that you've seen before, keeping in mind that lines 8 through to 14 are the trapezoidal approximation method. I won't go over the details. We saw them last Thursday. We saw them again on Monday. Lines 8 to 14, code you've seen before. Line 5 is the definition of the function we want to integrate, the curve under which we want to compute the area between specified limits. And you can almost read it off. It's the standard normal PDF. It's 1 on square root of 2 pi times e to the minus x squared on 2. So lines 1 through 14 define the function, the PDF, standard normal PDF, and the trapezoidal method for approximating it. Second half of the code, most of the action happens in lines 3 and 7. In line 3, we call the trapezoidal function with f, the standard normal PDF, the lower and upper limits of integration, a and b, and the number of panels that we want to use in the trapezoidal method to approximate the function. If you remember from Monday and last week, that as we make that number of panels larger, we get a better and better trapezoidal approximation. 100 is just fine here. And line 7, in line 6, we define the range of the x variables that we're going to use to plot the PDF. Notice here when I plotted it, the limits of the blue function are plus or minus 4. Actually, with a standard normal PDF, we could have made the limits 5 or 6 or 7. It wouldn't have made much sense to do that, because basically by the time we get to about 3 or 4, the blue curve has effectively reached 0. It never exactly reaches 0, but it gets very close. This is an engineering course, not a mathematics course. So by the time we're in within a fraction of a percent of 0, that's close enough. So the limit here on line 6 of the code, there's nothing special about the plus or minus 4. It's just enough to capture all the interesting behavior of the PDF. Line 7 is the second most interesting line on this page, which gives us the X range corresponding to the red shaded area. Because remember that what we're going to do is generate this plot. And this one, we need to focus in on the range between X equals 1, X equals 2, and that's done in line 7, where we generate linearly spaced points, 100 of them, between A equals 1 and B equals 2. And we do that because in line 10, we plot the function, the PDF, evaluated at the restricted range of X values, and we do it with a red line. So we're actually producing this segment of the PDF as a red line, and then this call to the very clever function that we saw on Monday called fill between. This actually allows us to shade in the area under the function evaluated on the restricted range, and to do it with a red color. And from then on, specifying the axis if you want to fine tune it, which I did, and then showing it. So let's have a look at that in code, standard normal.py. Here it is. Here's the code that you see on the screen in front of you now is the code that was split over 2 pages in the lecture notes. Standard normal PDF, trapezoidal function definition, and then the integration and the display of that function over the restricted range. So if we run that now, wrong function. Run standard normal. Look at that. It's exactly like it is in the lecture notes. Blue curve is the PDF, the bell-shaped curve. The red shaded area is the area under the curve between the limits of 1 and 2, just for the sake of a concrete example. And then a call to the trapezoidal function, which then displays on the console the area under the curve between x equals 1 and x equals 2. When it's the 4 decimal places, it's 0.1359. So that's the red shaded area. There we go. So just for fun, got a couple of minutes here. Just for fun, what happens if we specify the area between -1 and 2? It's red shaded area between -1 and 2. And now the probability of the random number falling in the range -1 to 2 is about 82%. What happens if we make that -3 up to 4, run it again? Now we've almost got the complete area under the curve. 99.9% of the area under the curve is captured between -3 and 4. And if we bump that down to -4 to 4, we'll get 100%, 99.99%. If we start fiddling with these ranges here, we'll get slightly different numbers. But the point is that effectively all the area under the curve is located between plus or minus 4. Good. We've got one more thing to do. This code computes that area. And I've said it a couple of times now, the area under the red shaded curve when over the limits of integration between 1 and 2, that area was 0.1359, obtained using the trapezoidal method, accurate to 4 decimal places. We can test that though. What we can do is generate a large number of these random numbers and check that the observed fraction of them between the ranges 1 and 2 really does match this theoretical result or the computational result using the trapezoidal method. So what we're going to do in the third and final bit of code is generate, I think it's a million random numbers, all satisfying this standard normal distribution, first parameter 0, second parameter 1. We're going to generate 1 million of them. And then in lines 8 through 11, we're going to use a for loop to run through the array of them. And every time the number satisfies, it falls within the range A to B, we'll keep a count. We generate 1 million of those numbers. We would expect the observed fraction to be pretty close to the theoretical probability, which is 0.1359, about 14%. So let's run that now. Our third and final. It's called standard normal demo. Here's the code, shared it with you in lecture notes, lecture code channel, also Python, also in Blackboard. Generate 1 million numbers, count up the number of them that fall within the range between 1 and 2. And then the observed fraction of numbers in that range is displayed here by calculating the number that we observed divided by the total number. And if we run that now, we observe that the fraction of random numbers in the range 1 to 2 is 0.1355. It's not exactly what we computed, but we wouldn't expect that either because there's still some randomness here. And because I haven't specified the random number seed in this example, if we run the code again, we get a slightly different fraction of observed numbers falling in that range. That only differs in about the 3rd decimal place. Do it again. This time it's 0.136, run it again, 0.1359 and so on. So it's pretty close, to the, I'll say the exact value obtained by numerical integration of the PDF, but it will differ. And the reason why it differs is because what we're effectively doing is producing a histogram like this. And you observe that even with 100,000 numbers and 100 bins, we don't get exactly a perfect standard normal PDF, nor would we expect to, but we would expect that as we keep drawing more and more samples and we use narrower bins, that histogram approximation will get better and better. So there we go. Quick lecture summary. What did we do today? I said we wanted to do two things. I wanted to show you how to draw random numbers using the normal function in the NumPy library. And then I wanted to show you how we could use numerical integration using the trapezoidal method, for example, to compute the probability for those standard normal distribution. In the old days, those probabilities weren't computed using numerical integration, but they were distributed in books or tables of numbers. These days, we can do it in a moment's notice on a computer, and I've shown you how to do that today. This normal distribution is arguably the most common distribution that occurs in all branches of engineering, and in fact, well beyond engineering into all the physical sciences and all the social sciences. In fact, if there was one distribution you could take to a desert island, it would be the normal distribution. The standard form that we've looked at today to introduce the ideas have been restricted in the choice of these parameters. And so we're going to look at what the effect of those two parameters is in Monday's lecture, and then look at some applications. And we'll actually see that those first two parameters shift where the central value of the bell curve is, and also the width of the bell curve. And if you can change those two factors, where the center value is and how wide the bell curve is, you've got a very powerful and very common probability density function that's used, as I say, right through engineering and the physical sciences. So that's all the lecture content I have for you today. Until we catch up on Monday morning, I'll say bye for now.